Okay, today's tutorial is quantum numbers. What they are, where they come from, what they're used for, and hopefully a clarification of what orbitals are. If you haven't already learned about orbitals, you should do so before looking at this tutorial. So if you think about the history of all the very, very large-brained people investigating what's inside the atom, there are a lot of famous scientists. But I think there's three in particular that are most relevant for today's discussion. First one, Werner Heisenberg, who told us that the more we know about the position of an electron, the less we can know about its momentum, and vice versa. The more we know about its momentum, the less we can know its position. In other words, what the electron is doing inside the atom is a very fuzzy concept. And this is called Heisenberg's uncertainty principle. There's a lot of uncertainty about what the electron is doing, and so we speak about the electron in terms of probabilities. And then you have Louis de Broglie. De Broglie told us that anything with mass also will have a wave property. But in our everyday experience, things with mass, like people or soccer balls, don't seem to have any wave properties whatsoever. And that is because the wave property, in this, which we will symbolize with the wavelength, is inversely proportional to the mass. And so if you have a very, very, very tiny mass, like an electron, then the wavelength or the wave property of that particle becomes quite significant. And so then, with that in mind, we have Schrödinger. Erwin Schrödinger with the umlauts. He came along and defined what the electron is doing inside the atom based on it being a wave and not a particle. And he defined what the electron is doing mathematically, and so we call that Schrödinger's equation. Now, the equation is very complicated math, but we can derive from the equation three quantum numbers symbolized n, l, and m sub l, as well as a fourth that came a little later, m sub s. And we will take a look at these in the rest of this presentation. What do each of these symbolize, and how are they related to what the electron is doing, what the orbitals are, and how the orbitals are oriented. Okay, so let's take a look at s orbitals and p orbitals. First up, the s orbitals. As we know, orbitals are always represented by a number and a letter. Well, the number is the principal quantum number, and that is our first quantum number, symbolized as n. The letter is our second quantum number, symbolized as L, and that tells us the shape of the orbital. But we are going to not talk about the shape at this moment. We will a little bit later. Let's first take a look at what the principal quantum number tells us. Here we have the principal quantum number going from 1 to 2 to 3. And what happens to the orbital as we go from n equals 1 to n equals 2 to n equals 3? It gets bigger. As n gets bigger, the orbital gets bigger. If you look at the p orbitals, 2p, 3p, 4p, when n equals 2, we have this sized orbital, n equals 3 a bigger orbital, and n equals 4 an even larger orbital. So there's a direct relationship to how far away the electron is from the nucleus and the principal quantum number. And that is because the energy of the electron increases as the principal quantum number increases, and because the electron has more energy, on average it's going to be further from the nucleus and therefore occupy a space that is larger. And that larger space is shown here as the surface of the orbitals getting larger. Now let's take a look at L, the angular momentum quantum number. This determines the shape of the orbital. And as you can see, the S shape is quite different than the P shape. But we are talking about quantum numbers, not letters. So in fact, each letter has a corresponding number. 0 represents the S orbital. When L equals 1, that's the P orbital. L equals 2 is the D shape. 3 is F. And when L equals 4, we have G orbitals. Note that L can be any integer from 0 to n minus 1. So for example, if we have a principal quantum number of 3, then L can have any shape from 0, which is S, or 1, which is P, or 2, which is D. So that 0, 1, and 2 are 0 to n minus 1. What about if n equals 2? L can be any orbital from 0 or 1, in other words, S or P. And if n equals 1, L can only be 0 or S. And the third quantum number, the magnetic quantum number, m sub L. Here, we can see that the three p orbitals exist in different orientations in three-dimensional space, and that is what the magnetic quantum number m sub L is telling us. M sub L can be any integer from negative L to positive L, and each integer represents a different orientation in space. For example, if L equals 1, in other words, P, then M sub L can be any number from negative L to positive L, any integer, and so therefore we have negative 1, 0, and positive 1 as possible M sub L numbers. That's a total of 3 numbers, and that's exactly how many orbitals we find in the p orbital at any one energy level. And these 3 orbitals are oriented perpendicular to each other on the XYZ axes, and we can see that when you look at the 3 orbitals simultaneously. And finally, we have the spin quantum number, m sub s. And this derives from the fact that experimentally, electrons in the same orbital are found to deflect in opposite directions when going through the same magnetic field. And those 2 electrons are designated as either positive 1/2 or negative 1/2. They are said to have opposite spin. So for example, in the 2s orbital, let's say you have 2 electrons. One will have a spin of positive 1/2, the other one will have a spin of negative 1/2. Another example, 3p. If there's 2 electrons in one of those 3p orbitals, they will have opposite spins, positive and negative 1/2. And the spin quantum number allows us to say that no 2 electrons in any one atom can have the same set of quantum numbers. For example, let's look at the quantum numbers that represent the 2 electrons in 3p. N equals 3 when in 3p. L equals 1, that's p, right? M sub L can be anywhere from negative 1, 0, or positive 1. We'll just pick one and say it can be 0. So what is going to distinguish these 2 electrons, finally, is the m sub s. One of them will be positive 1/2, and the other one will be negative 1/2. And so you'd never have 2 electrons with the same 4 quantum numbers in an atom. One very, very important thing, we need to lay a misconception to rest, and that is that the principal quantum number, also called the principal energy number, represents the actual energy of the electron. That is only true in hydrogen. In every other element, that is not true. The energy of the electron is represented by both the principal quantum number as well as the angular momentum quantum number, L. So the L value in this case 1, and the n value, in this case 2, together represents the energy of the electron. So a 2p electron will have a different energy than a 2s electron. Hydrogen is different because it only has one electron. There are no repulsions, there's no penetration of electrons to the nucleus in a single electron atom, and so it is only the principal quantum number that actually designates the electron's energy in the hydrogen atom. Once you have more than one electron, you start getting these repulsions and penetrations, and that separates the energies of the electrons in the different orbitals. And an important term that we should take a look at is the word sublevel. And sublevel is commonly used to refer to the specific orbital that an electron is existing in. For example, you can have an electron in the sublevel 2s or 3s or 3p. And so the sublevel refers to both the principal quantum number as well as the angular momentum, the L value, together. And so therefore the sublevel represents the energy of the electron in any element other than hydrogen. Let's take a look at the surface boundaries and three-dimensional orientations of the 5d orbitals. So here, again presented on the XYZ axes, we can see that every one of these orbitals has a different orientation in three-dimensional space. So notice that there are 5 orbitals at the d level, and we can use quantum numbers to understand why that would be the case. We know that at the d orbital, the quantum number is 2, and the orientations, m sub L, are going to be negative L to positive L. So if that's the case, the possibilities are negative 2, negative 1, 0, positive 1, and positive 2. These are the possibilities for the orientations in space. There's 5 possibilities for orientations of d orbitals in three-dimensional space. And that's exactly what we see, 5 orbitals at any one energy level. Let's take a look at the surface boundaries and three-dimensional orientation of the 7f orbitals. Here we're given an illustration of the 7f orbitals, and we know that for the L value, f is equal to 3, and that we know therefore with m sub L being equal to anywhere from negative L to positive L, what are the values that we get? Negative 3, negative 2, negative 1, 0, positive 1, positive 2, and positive 3. So here we have 7 possible orientations in three-dimensional space. And that's exactly how many f orbitals there are at any one quantum number that allows for enough energy to have f orbitals in existence. Right. Why is the principal quantum number limited to integers between 0 and 7? Well, if you look at the periodic table, the periods are numbered, and the periods represent the principal quantum number of the outermost, in other words, valence electrons. And so if you see the amount of elements that are on the periodic table, we can't go any higher than 7. Each period number represents where the outermost electrons are for the elements in that period. And so you can see that there is nothing under francium and radium, and so therefore we do not have any outer electrons that are at principal energy level 8. So therefore n is confined to integers between 0 and 7.